In this video, I will describe some of the causes and effects of cavitation failure. These pictures show examples of the type of damage that is caused by cavitation. This is a picture of a large Kaplan-style turbine runner that is now removed from service at a hydroelectric power generation facility. On the low-pressure side of the turbine blade, in approximately this location, we can see some evidence of the type of surface pitting that is typical of cavitation damage. Another example of cavitation is located in approximately this area of the blade tip of the turbine runner. This next example is also of a hydroelectric facility. This particular facility dates back to the early 1900s and is now abandoned. This is a picture of a horizontal turbine housing. If we look inside the housing, about here, we can see the results of cavitation and erosion that occurred over the years of service. Also, notice that if you look closely, you may be able to see what appears to be the results of a brazing process repair in a couple of locations that occurred sometime in the past. In order to understand how a moving fluid can cause the type of damage that we have seen in these examples, it is helpful to review a few basics of fluid dynamics. This graph is known as a vapor pressure graph. A vapor pressure graph shows the relationship between the temperature and pressure of a fluid. This particular graph is produced from data that is specific to water. However, similar looking vapor pressure graphs are available for all fluids. Notice the vertical axis, or the y-axis of the graph, is used to plot the pressure of the water, and the horizontal axis, the x-axis, is used to plot the corresponding temperature. Notice that this upper portion of the graph is labeled as a liquid, and that this lower section is a vapor, or a gas. This line is known as the vapor pressure line, or the vapor pressure curve, and it identifies the point of transition from a liquid to a gas, the process that we typically call boiling. Remember this term vapor pressure line, as I will refer to it again in a moment. To see how this graph works, let's use a couple of examples. For example, many people, when asked if they know the boiling temperature of water, will answer that it boils at 212 degrees Fahrenheit. This answer is partially correct. As shown by the graph, water does boil at 212 degrees Fahrenheit at the standard atmospheric pressure at sea level of 14.7 psi. However, notice that the boiling temperature of water changes with its pressure. In general, lower boiling temperatures correspond with lower pressures, and higher boiling temperatures correspond with higher pressures, as we can see on the graph. Typically, if we want to boil water, we add heat in order to raise its temperature until it reaches the boiling point. We can demonstrate this process on the vapor pressure graph. Let's say, for example, that we pick a point at random on the graph. Let's say that it is right there. If we cause the water that is at that temperature and pressure to boil by raising its temperature, we can graph that by drawing this straight line, by starting at its current temperature and pressure and ending at the boiling point. Here is a short animation that visually illustrates this process. In this animation, this part represents a cylinder, and it is partially filled with water, shown here. This represents a piston. Imagine that the piston is tightly fitted to the cylinder so that there are no leaks in the system. Now, as we add heat to the cylinder, the temperature of the water will increase, as expected, and at some point will begin to boil. During the boiling process, the water changes phase from a liquid to a gas, otherwise known as steam. Now, as I start the animation, we can see that the expanding steam in the system raises the piston, as expected. Now, I'll pause the animation momentarily. At this point, notice that our system contains a liquid, water, a gas, the steam or water vapor, and also these bubbles that are in the process of transitioning from a liquid to a gas. exactly as we saw in the vapor pressure graph. In the next step of the animation, I'll turn off the heat to allow the water to cool. Notice that as this happens, that the gas bubbles will return to their liquid state. This process of changing phase from a gas to a liquid by cooling is known as condensation. Let's resume the animation and watch what happens. Now if we go back to the vapor pressure graph, we have just seen the process of causing water to boil by adding heat. This is a process that is very familiar to us. Now for something that isn't so familiar, by looking at the graph, we notice that it is also possible to cause the water to boil without adding any heat at all. That is, by simply lowering its pressure. If we show that process on the graph, the line would look something like this. Returning again to our earlier animation, we'll see how this process is different from the one that we showed previously. Here we have the same setup that we had earlier, the same cylinder, water, and piston. Except in this example, instead of heating the water, we will actually lower the pressure in the cylinder by pulling upward on the piston, like this. Again, as before, I'll pause the animation midway through the process so that we can see what is happening. Notice that, just as was the case in our earlier example, our cylinder contains water and water vapor. It also contains gas bubbles that are in the process of changing phase from a liquid to a gas. Everything looks exactly as it did previously, except that we got to this point, in this case, by lowering the pressure acting on the water, not by heating it. In the next phase of the animation, I'll reverse the force acting on the piston so that it recompresses the contents of the cylinder. As the pressure increases, notice that the gas bubbles collapse under the increasing pressure as they return to a liquid phase. This rapid collapse, also called an implosion, of gas bubbles under pressure is the basis for understanding how cavitation damage is caused. Okay, I'll resume the animation and repressurize the cylinder. Going back again to the vapor pressure graph, we have seen that water can be caused to boil by either adding heat or by lowering its pressure. Obviously, it's also possible to cause the water to boil by any combination of changes to its temperature and pressure, such as this, for example. Okay, so let's see how this applies in an actual application. This is an example of an end suction centrifugal pump. To identify some of the parts of the machine, this is the inlet or the suction end of the pump, and this is the outlet or the discharge. And if we zoom in closely, we can see the rotating impeller. This area is known as the eye of the impeller. And if I pause the impeller for a moment, we can see some evidence of cavitation damage modeled into the impeller, as shown here. In this next example, I'll show how this type of cavitation damage occurs. Here again is the picture of the pump with the areas that we just identified: the suction, the eye of the impeller, and the discharge. And here is a beginning of a pump curve that I started. On the horizontal axis of the graph, I'll chart the flow of the fluid as it moves through the pump. I'll call this location the suction portion of the pump, and the discharge location here, and the location at the eye of the impeller here. On the vertical axis of the graph, I'll chart the corresponding pressure of the fluid at different locations in the pumping cycle. Let's say that the suction pressure is at this location, and the pressure at the eye of the impeller is at this location, lower than the suction pressure, and the discharge pressure is here. So by connecting the dots, the typical pump curve looks something like this. Let's use this graph to see how the cavitation process works. Remember the vapor pressure line that we discussed earlier? Let's assume, using the fluid in this example, that the boiling pressure of the fluid happens to be at this particular pressure. In this example, cavitation should not be a concern. Why not? Well, because the lowest pressure in the pump curve, located here, is higher than the boiling pressure of the fluid in this example. Okay, let's try a different example. In this case, let's assume that the boiling pressure is located here, higher than previously. Again, you can think of this as the line at which boiling occurs. Everything above this line is a liquid, and below the line is a vapor. Notice this area right here where the pump curve line is lower than the vapor pressure line. This is the area where gas bubbles are being formed in the fluid. And at this location is the point where the gas bubbles collapse. At this point, the gas bubbles are unable to remain as a gas. They become compressed and collapse under the increasing pressure and quickly change phase from a vapor back to a liquid. In the pumped fluid, the time from the creation of gas bubbles until the time of their collapse happens very quickly, in just a fraction of a second. This process, the rapid formation and subsequent collapse of gas bubbles in a fluid, is known as cavitation. You might be wondering how all of that damage that we saw earlier could be caused by having gas bubbles in the fluid. And the answer to that is, for the most part, the damage is not caused by the gas bubbles themselves, but by the collapse of the gas bubbles at this point of the process. Let's use an illustration to show how the collapse of gas in a fluid can cause the pitting damage that we saw earlier. Assume that this block represents a pump impeller where cavitation is occurring. And there is fluid here, and this is a gas bubble that has formed in the fluid. The fluid is under pressure, as represented by these arrows acting on the gas bubble. And the gas bubble itself has a vapor pressure, as we saw earlier, that opposes the fluid pressure as shown here. During the process, the pressure of the fluid increases to the point that the gas bubble collapses rapidly under the increasing fluid pressure. This rapid collapse or implosion of the gas bubble is the cause of much of the damage that occurs during cavitation. Let's take a look at this short animation to help illustrate how this gas bubble collapse causes the damage that it does. In this animation, this plate represents a part that is being damaged by cavitation. The inflated balloon represents a gas bubble that is formed in the fluid, and this weight represents the fluid pressure that acts on the surface of the gas bubble. Notice that the balloon is able to support a certain amount of weight, but at some point the balloon is no longer able to support the increasing weight and eventually collapses under the load. And having lost its support, the weight crashes down on the surface of the part. Returning now to our earlier illustration, similar to the collapsing balloon that we just saw, As the pressure of the fluid increases during the pumping cycle, at some point the vapor pressure inside the gas bubble is unable to support the external fluid pressure of the surrounding liquid. At that point, the gas bubble collapses or implodes under the pressure, or in other words, the gas bubble vapor quickly changes phase back to a liquid state. The collapsing gas bubble results in a high-velocity, localized fluid impact shock wave on the surface of the part. By some estimates, that fluid impact pressure is calculated to be as high as 60,000 psi. Pressures in that range are capable of plastically deforming some metals. It is important to remember that this process is not a one-time isolated event. Over time, the continual pounding of the fluid impact destroys the surface material at that location, and the resulting pitting in the surface of the part is known as cavitation damage. Thanks for watching. RepairEngineering.com